The light from the first stars traveled for billions of years across the unfathomable expanse of the cosmos, finally reaching us here on Earth. These ancient beams are more than just light, they are messages from the dawn of the universe itself, carrying secrets about how everything we know began. Picture the universe in its infancy, a dark and formless void, until the first stars ignited, scattering brilliance across the darkness. From those early flickers to the sprawling galaxies we see today, the cosmos has been on an extraordinary journey of transformation. But what can these ancient lights tell us about where we came from? What mysteries do they hold about the forces that shaped the stars, planets, and even life itself? In this video, we'll embark on a voyage through time and space, tracing the evolution of the universe from its earliest moments to the intricate galactic structures that define our modern skies. Together, we'll uncover the stories written in starlight and explore the questions that still puzzle astronomers today. This is more than a journey, it's a chance to witness the universe as it was, as it is, and as it might one day become. So, buckle up and get ready to explore the celestial realms like never before. Long before galaxies painted the night sky, the universe was a vast, silent expanse cloaked in darkness. This era, known as the Cosmic Dark Ages, began just moments after the Big Bang, when the universe was filled with nothing but a thick fog of hydrogen and helium gas. No stars, no galaxies, just an endless sea of potential waiting to be unlocked. But in that stillness, something extraordinary was brewing. Gravity, the silent architect of the cosmos, began to pull these gases together, slowly gathering them into dense clouds. Over millions of years, these clouds grew heavier and hotter, until finally the first stars burst into existence, piercing the darkness with their brilliant light. These early stars were unlike anything we see today. Imagine fiery giants, hundreds of times more massive than our sun, burning with an intensity that's almost impossible to comprehend. But their lives were fleeting like cosmic fireworks. They blazed brightly for just a few million years before meeting a dramatic end. Yet in their short lifespans, they did something incredible. Deep within their cores, nuclear fusion forged heavier elements like carbon, oxygen, and iron elements that would later become the building blocks of planets, moons, and even life itself. When these ancient stars exhausted their fuel, they didn't fade quietly. Instead, they exploded in colossal supernovae, scattering their newly forged elements across the universe. This cosmic recycling process seeded the cosmos with the raw materials needed for the next generation of stars and galaxies. Without these early giants, the universe, as we know it, might never have taken shape. Their fiery deaths were not an end, but a beginning, a foundation upon which the intricate tapestry of galaxies could begin to weave itself. And as we'll see, this explosive legacy would set the stage for the next chapter in the story of the cosmos. The deaths of these ancient stars were anything but quiet. When the first stars exhausted their fuel, their cores collapsed under their own immense gravity, triggering explosions so powerful they outshone entire galaxies. These supernovae were cosmic fireworks on a scale beyond imagination, releasing energy in blinding bursts that rippled through the universe. Shockwaves tore through the surrounding gas, compressing it and heating it to unimaginable temperatures. In the heart of these explosions, something extraordinary happened. The intense heat and pressure forged elements heavier than hydrogen and helium, carbon, oxygen, iron, and more elements that had never existed before in the universe. These newly created elements were hurled into the void, scattering across vast distances like seeds sown by a cosmic gardener. Over time, they mingled with the surrounding gas, enriching it with the raw materials needed for the next generation of stars and planets. Without these supernova, the universe would have remained a barren place, devoid of the diversity we see today. Every atom of carbon in your body, every molecule of oxygen you breathe, can trace its origins back to these ancient explosions. They were not just destructive events, they were the universe's way of recycling itself, turning the ashes of dying stars into the building blocks of life. But the story doesn't end there. The shockwaves from these supernovae didn't just scatter elements, they also triggered the birth of new stars. As the waves rippled through the gas clouds, they compressed them, creating dense pockets where gravity could take hold. Slowly, these clouds began to collapse, forming the seeds of future stars. It's a cycle as old as the universe itself. Stars are born, they live, they die, and from their ashes, new stars rise. This process, repeated over billions of years, has shaped the galaxies we see today, each one a testament to the creative power of destruction. As we gaze at the night sky, it's humbling to think that every star, every planet, every speck of dust has its origins in these ancient explosions. The universe is a cosmic crucible, constantly transforming itself through cycles of creation and destruction. And as we'll see next, the aftermath of these supernovae set the stage for the formation of galaxies, the grand structures that define our modern universe. The remnants of those ancient supernovae didn't just drift aimlessly through the cosmos. Instead, they became the seeds of something far greater, the first galaxies. Gravity, the invisible hand that shapes the universe, began to pull these scattered elements together, creating dense clouds of gas and dust. But gravity didn't work alone. A mysterious force, one we still don't fully understand, played a crucial role in this cosmic construction. Dark matter, though invisible and undetectable by conventional means, dark matter's gravitational pull acted as the scaffolding upon which the first galaxies were built. Without it, the universe might have remained a formless expanse, devoid of the intricate structures we marvel at today. Imagine a vast, invisible web stretching across the early universe, its threads made of dark matter. This web acted like a cosmic blueprint, guiding the movement of gas and dust into denser regions. As these materials gathered, they began to collapse under their own gravity, forming the first stars and eventually entire galaxies. These early galaxies were unlike the majestic spirals and ellipticals we see today. They were chaotic, irregular, and teeming with activity. Star formation rates were off the charts, with new stars igniting at a pace that would make modern galaxies seem almost dormant by comparison. The universe was in its wild youth, and these early galaxies were its first experiments in structure and order. But what made these galaxies so different? For one, they were smaller and more compact, with stars packed tightly together. Their irregular shapes reflected the turbulent environment in which they formed, with gravity pulling them in multiple directions at once. And because they were rich in gas and dust, they were veritable factories of star creation. Intense bursts of star formation lit up these galaxies, their light piercing the darkness of the early universe. Yet, despite their chaotic nature, these galaxies were the building blocks of everything we see today. They were the first steps in a journey that would lead to the vast, organized structures we now call home. As these early galaxies evolved, they began to merge and collide, their gravity pulling them together in a cosmic dance that continues to this day. Over billions of years, these collisions would transform the irregular, chaotic galaxies of the early universe into the majestic spirals and ellipticals that dominate our modern skies. But that's a story for another part of our journey. For now, let's marvel at the incredible process that turned the scattered remnants of ancient stars into the first galaxies, setting the stage for the universe as we know it. As the first galaxies took shape, another enigmatic force began to emerge from the cosmic shadows: supermassive black holes. These colossal entities, lurking at the hearts of galaxies, are far more than just destructive voids. They are cosmic architects, playing a pivotal role in shaping the very fabric of their galactic homes. But how did these giants form, and what makes them so influential in the story of galactic evolution? The answers lie in the turbulent hearts of young galaxies, where gravity and chaos intertwine to create something truly extraordinary. In the early universe, as galaxies coalesced from swirling clouds of gas and dust, dense pockets of matter began to collapse under their own gravity. Some of these pockets grew so massive that nothing, not even light, could escape their grasp. These were the seeds of supermassive black holes, growing rapidly as they devoured surrounding material. But their hunger didn't just consume, it also created. As matter spiraled into these black holes, it heated up to incredible temperatures, releasing torrents of energy that lit up the cosmos. These active black holes became the engines behind quasars, the brightest objects in the universe, shining with the light of 1 trillion stars. Quasars are more than just cosmic beacons, they are windows into the past. Their intense light, traveling billions of years to reach us, reveals the conditions of the early universe, but their brilliance also tells another story, one of balance and regulation. The energy unleashed by quasars doesn't just radiate outward, it also interacts with the surrounding galaxy. This energy can heat up gas clouds, preventing them from collapsing to form new stars. In this way, supermassive black holes act as cosmic regulators, controlling the rate of star formation and shaping the growth of their host galaxies. It's a delicate dance. Too much energy and star formation halts, too little, and the galaxy becomes a chaotic frenzy of unchecked stellar birth. The influence of supermassive black holes extends far beyond their immediate surroundings. Their gravitational pull can warp the very fabric of space-time, altering the paths of stars and gas clouds. In some cases, they even trigger the merging of galaxies, as their immense gravity pulls neighboring galaxies into a cosmic collision. These mergers can reignite star formation, creating bursts of new stars and reshaping the structure of the galaxies involved. It's a process that continues to this day, with supermassive black holes still playing a central role in the evolution of modern galaxies. Yet, for all we've learned, black holes remain shrouded in mystery. How do they grow so massive, so quickly? What exactly happens at the edge of their event horizons? And how do they maintain such a precise balance between creation and destruction? These questions drive astronomers to peer deeper into the cosmos, searching for clues in the light of ancient quasars and the swirling disks of modern galaxies. As we uncover more about these enigmatic giants, one thing becomes clear: they are not just cosmic anomalies, they are fundamental to the story of the universe itself. And as we'll explore next, their legacy continues to shape the galaxies we see today, leaving an indelible mark on the cosmic landscape. The universe, in its grand design, is far more interconnected than it appears at first glance. What seems like random scatterings of galaxies across the night sky is actually part of an intricate, sprawling network known as the cosmic web. Picture this: trillions of galaxies, vast clouds of gas, and invisible threads of dark matter woven together into a structure so immense it defies comprehension. This cosmic web stretches across the universe like a spider's silk, connecting galaxies and galaxy clusters in a delicate balance of gravity and motion. But how did this colossal network come to be? The story begins in the earliest moments of the universe, long before galaxies even existed. In the aftermath of the Big Bang, the universe was a seething, chaotic soup of energy and matter. Tiny fluctuations in density regions where matter was just slightly more concentrated began to ripple through this primordial soup. These fluctuations were minuscule, no more than faint whispers in the fabric of space-time. Yet over billions of years, gravity amplified these whispers into something extraordinary. The denser regions pulled in more matter, growing larger and more pronounced, while the less dense areas emptied out, creating vast voids. This tug of war between attraction and emptiness shaped the cosmic web, turning those faint ripples into the backbone of the universe itself. To grasp the scale of this structure, think of it like a neural network, a vast, interconnected system where galaxies are the nodes and the threads of dark matter are the pathways. Or imagine a spider's web, glistening with dew in the early morning light. Each strand is a filament of galaxies and gas, stretching across millions of light years, while the intersections are dense hubs where galaxies cluster together. These clusters, some of the largest structures in the universe, are the bustling cities of the cosmic web. Hundreds, even thousands of galaxies can be found in a single cluster, bound together by gravity and surrounded by halos of dark matter. They are the anchors of the web, holding the entire structure in place. But the cosmic web isn't static, it's a dynamic, ever-evolving system. Galaxies move along the filaments, drawn toward the clusters by gravity's relentless pull. As they travel, they collide, merge, and interact, creating bursts of star formation and igniting the hearts of galaxies with supermassive black holes. The web itself continues to grow, stretching and expanding as the universe itself does. It's a living, breathing network, constantly reshaped by the forces that govern the cosmos. What's truly remarkable is how much of this structure remains hidden from view. Dark matter, the invisible glue that holds the web together, makes up the majority of its mass. We can't see it directly, but its gravitational effects reveal its presence, guiding the motion of galaxies and shaping the web's intricate patterns. Without dark matter, the cosmic web, as we know it, simply wouldn't exist. It's a reminder that much of the universe's majesty lies in what we cannot see, hidden in the shadows yet vital to the story of everything. As we continue our journey, we'll explore how these galaxy clusters, the great crossroads of the cosmic web, play a pivotal role in shaping the universe. They are more than just gatherings of stars. They are the beating hearts of the cosmic network, driving its evolution and revealing the profound interconnectedness of all things. From the tiniest fluctuations in the early universe to the vast, shimmering web that spans the cosmos, the story of the universe is one of connection, balance, and endless wonder. Galaxy clusters are the titans of the cosmos' vast metropolises where thousands of galaxies gather, bound together by the unyielding grip of gravity. These clusters are not just random gatherings, they are the most massive structures in the universe, each one a bustling hub of activity, teeming with stars, gas, and the invisible presence of dark matter. Imagine a city skyline, but instead of skyscrapers, you see galaxies of all shapes and sizes, swirling in a cosmic dance that has lasted billions of years. These clusters are more than just collections of galaxies. They are the beating hearts of the cosmic web, anchoring the great network that spans the universe. At the center of these clusters lies a mystery that defies easy explanation. Hot gas, heated to millions of degrees, glowing faintly in X-ray light. This gas, often referred to as the intracluster medium, fills the spaces between galaxies, creating a diffuse atmosphere that permeates the entire cluster. But how does it get so hot? The answer lies in the immense gravitational pull of the cluster itself. As galaxies move through this environment, their motion stirs the gas, generating shockwaves that heat it to incredible temperatures. This hot gas isn't just a byproduct. It plays a crucial role in the cluster's evolution, influencing star formation and the growth of galaxies within it. Yet the gas is only part of the story. Dark matter, that invisible and enigmatic substance, makes up the majority of a cluster's mass. Its gravitational pull holds the cluster together, acting as the cosmic glue that keeps galaxies from drifting apart. Without dark matter, these colossal structures would simply fly apart, their galaxies scattering into the void. The presence of dark matter isn't just inferred, it's revealed by the way galaxies move within the cluster, their motions betraying the unseen hand that shapes their paths. But even these titanic structures aren't immune to change. Galaxy clusters are dynamic, ever-evolving entities, and sometimes they collide. When two clusters meet, the result is one of the most energetic events in the universe. The collision releases staggering amounts of energy, heating the gas to even higher temperatures and creating shock waves that ripple through the cluster. These collisions can also strip gas from galaxies, altering their evolution and leaving behind ghostly trails of material. It's a cosmic spectacle, a reminder that even the largest structures in the universe are shaped by forces beyond our everyday experience. And yet, there's another force at work, one that influences not just galaxy clusters but the entire universe: dark energy. This mysterious force, discovered only in the late 20th century, is causing the expansion of the universe to accelerate. It's as if the universe itself is being pulled apart by an invisible hand, stretching the cosmic web and driving galaxy clusters further apart. Dark energy's influence is subtle but profound, shaping the fate of the universe on the grandest scales. As we delve deeper into the story of the cosmos, this enigmatic force will take center stage, challenging our understanding of the universe and its ultimate destiny. But for now, let's marvel at the immense structures that galaxy clusters represent, a testament to the power of gravity, the mysteries of dark matter, and the dynamic nature of the cosmos itself. As we peer deeper into the cosmos, we encounter one of its most profound mysteries: dark energy. Unlike gravity, which pulls everything together, dark energy seems to do the opposite. It's an invisible force pushing the universe apart, stretching it faster and faster over time. This discovery, made in the late 20th century, turned our understanding of the universe on its head. For decades, scientists believed the universe's expansion was slowing down, destined to either stabilize or collapse back on itself. But dark energy revealed a startling truth: the universe isn't just expanding, it's accelerating. Imagine blowing up a balloon, but instead of slowing down as it grows, it inflates faster and faster, defying all expectations. That's the puzzling reality we now face. So, how did we uncover this mysterious force? The story begins with distant supernova, the brilliant explosions of dying stars. Astronomers used these cosmic beacons as mile markers, measuring their brightness to calculate how far away they were, but what they found was astonishing. The light from these supernovae was dimmer than expected, suggesting they were farther away than predicted. This could only mean one thing: the space between us and these stars was stretching faster than anyone had anticipated. It was as if the universe itself had stepped on the gas pedal, and dark energy was the unseen driver behind the wheel, but supernova weren't the only clue. The cosmic microwave background, the faint afterglow of the Big Bang, also holds secrets about dark energy. Tiny fluctuations in this ancient light reveal the universe's early structure and how it has evolved over billions of years. By studying these patterns, scientists have confirmed that dark energy makes up a staggering 68% of the universe's total energy. Yet, despite its dominance, we still know very little about what dark energy actually is. Is it a property of space itself, a new kind of field or particle, or something entirely beyond our current understanding? These questions remain at the forefront of cosmological research, challenging us to rethink the very fabric of reality. The implications of dark energy are as profound as they are puzzling. If the universe continues to accelerate, distant galaxies will eventually move so far away that their light can no longer reach us. Over trillions of years, the night sky could grow darker and darker, leaving future civilizations with a universe that feels eerily empty, but dark energy's influence doesn't stop there. It also shapes the fate of galaxy clusters, the largest structures in the cosmos. As the universe expands, the delicate balance between gravity and dark energy determines whether these clusters will continue to grow or be pulled apart by the relentless push of acceleration. What's truly remarkable is how this discovery has reshaped our view of the cosmos. Dark energy reminds us that the universe is far more dynamic and mysterious than we ever imagined. It's a force that defies simple explanation, yet its effects are written across the fabric of space-time, from the smallest galaxies to the largest structures in existence. As we continue to explore this enigmatic force, one thing is certain: dark energy holds the key to understanding not just the universe's past, but its ultimate destiny. And as we'll see next, this journey into the unknown is far from over. The universe, as vast and mysterious as it is, isn't immune to the passage of time. Its fate, shaped by the invisible hand of dark energy, remains one of the most profound questions in cosmology. Will the cosmos continue to expand forever, cooling into an eternal, silent void, or could something more dramatic lie ahead, a cataclysmic event that rips apart the very fabric of reality? These aren't just speculative musings, they're possibilities grounded in our current understanding of physics, each one painting a strikingly different picture of how the universe might end. One of the most widely discussed scenarios is the Big Freeze, also known as the heat death of the universe. Imagine a future where the expansion driven by dark energy continues unabated, stretching galaxies further and further apart. Over trillions of years, stars will burn out, galaxies will fade, and the universe will grow colder and darker. Eventually, even the energy needed to sustain life or light, a single star will dissipate, leaving behind a vast, lifeless expanse. This isn't a sudden, dramatic event, it's a slow, inexorable decline, a cosmic twilight that stretches into eternity. Yet, even in this cold, dark future, the universe isn't truly dead. It's simply reached a state of maximum entropy, where energy is evenly distributed and no work can be done. It's a hauntingly beautiful end, one that speaks to the inevitability of change and the impermanence of all things. But what if the universe's fate isn't so gentle? Another possibility, known as the Big Rip, offers a far more violent conclusion. In this scenario, dark energy doesn't just push galaxies apart, it grows stronger over time, eventually overcoming even the forces that hold atoms together. Picture this: first, galaxies are torn from one another, then stars are ripped from their orbits, and finally, even the bonds between particles are shattered. The universe, once a tapestry of intricate structures, is reduced to a chaotic sea of isolated particles. The Big Rip isn't just the end of the universe as we know it, it's the end of matter itself. It's a dramatic, almost poetic finale, one that underscores the fragility of existence and the immense power of the forces that shape our reality. These scenarios aren't just scientific curiosities, they invite profound philosophical reflection. If the universe is destined to end in cold, silent darkness or violent dissolution, what does that mean for us, for our place in the cosmos? These questions remind us that existence, on the grandest scales, is fleeting. Yet, they also highlight the extraordinary privilege of living in a time when the universe is vibrant and full of wonder. We are here, for a brief moment, to witness its beauty and unravel its mysteries. To explore these questions further, we rely on the cutting-edge tools and technologies that allow us to peer into the deepest corners of the cosmos. Telescopes like the Hubble Space Telescope and the James Webb Space Telescope capture light from billions of years ago, revealing the universe's past and hinting at its future. Ground-based observatories, equipped with advanced instruments, measure the subtle effects of dark energy on the expansion of the universe, and particle accelerators, like the Large Hadron Collider, recreate the extreme conditions of the early universe, helping us understand the fundamental forces at play. These tools are more than just scientific instruments, they are windows into the unknown, allowing us to piece together the story of the cosmos and glimpse its ultimate fate. As we continue to explore, one thing becomes clear: the universe is a place of both wonder and uncertainty. Its fate, shaped by forces we are only beginning to understand, remains an open question. But in asking these questions, in seeking to understand the cosmos, we find something even more profound: a connection to the vast, intricate web of existence that binds us all. And that, perhaps, is the greatest mystery of all. For centuries, humanity's understanding of the cosmos was limited by the reach of our eyes and the tools we could build. But with the invention of the telescope, everything changed. Suddenly, the distant stars and galaxies that once seemed forever out of reach became tangible, their secrets waiting to be uncovered. Today, telescopes both on the ground and in space are our windows to the universe, revealing its deepest mysteries and reshaping our understanding of everything from the first stars to the farthest reaches of the cosmos. These incredible instruments have become the backbone of modern astronomy, allowing us to peer billions of years into the past and witness the birth of galaxies, the death of stars, and the evolution of the universe itself. Among these marvels of engineering, few are as iconic as the Hubble Space Telescope. Launched into orbit in 1990, Hubble has transformed our view of the cosmos, capturing images of breathtaking beauty and profound scientific significance. From the swirling arms of distant galaxies to the delicate wisps of nebulae where stars are born, Hubble's observations have become a cornerstone of astronomical research. Its ability to peer deep into the universe has allowed scientists to study the earliest galaxies, shedding light on how they formed and evolved over billions of years. Hubble's images aren't just scientific tools, they're works of art that inspire wonder and curiosity, reminding us of the vastness and beauty of the cosmos. But Hubble is just the beginning. Enter the James Webb Space Telescope, a revolutionary successor that has taken our exploration of the universe to unprecedented heights. Launched in late 2021, Webb operates in the infrared spectrum, allowing it to see through the dust and gas that obscure visible light. This capability is especially crucial for studying the first stars and galaxies, which are so distant that their light has been stretched into the infrared by the expansion of the universe. Already, Webb has delivered stunning images and groundbreaking discoveries, from the chemical composition of distant exoplanet atmospheres to the intricate details of star-forming regions. Together, Hubble and Webb form a powerful duo, each complementing the other's strengths and expanding our view of the cosmos. Yet, not all telescopes are in space. Ground-based observatories, perched on remote mountaintops and deserts, play an equally vital role in our exploration of the universe. Instruments like the Very Large Telescope in Chile and the Keck Observatory in Hawaii use advanced adaptive optics to counteract the blurring effects of Earth's atmosphere, delivering images with remarkable clarity. These observatories have helped map the distribution of dark matter, measure the expansion rate of the universe, and even capture the first image of a black hole. By combining the power of space-based and ground-based telescopes, astronomers can tackle some of the most challenging questions in cosmology, from the nature of dark energy to the origins of the first stars. But how do telescopes go beyond capturing beautiful images? The answer lies in a powerful tool called spectroscopy. By breaking down the light from celestial objects into its component colors, spectroscopy reveals the chemical composition, temperature, and motion of stars, galaxies, and even the gas between them. It's like turning a telescope into a cosmic fingerprint scanner, allowing us to read the unique signatures of elements and molecules across the universe. Spectroscopy has been instrumental in discovering exoplanets, understanding the life cycles of stars, and even detecting the faint echoes of the Big Bang. It's a testament to how far we've come, from simply observing the heavens to decoding the very language of the cosmos. As we continue to push the boundaries of technology, the next generation of telescopes promises to unlock even more secrets. Projects like the Extremely Large Telescope and the Nancy Grace Roman Space Telescope are poised to revolutionize our understanding of the universe, offering sharper views and deeper insights than ever before. These advancements aren't just about bigger mirrors or more sensitive detectors. They're about expanding the horizons of human knowledge, revealing the universe in ways we've only begun to imagine. And as we'll explore next, the story of the cosmos is far from over. With each new discovery, we're reminded that the universe is a place of endless wonder, waiting for us to uncover its next chapter. As we gaze at the stars, the light reaching our eyes carries more than just beauty. It holds the secrets of the cosmos itself. Hidden within that light are clues about the composition, temperature, and motion of celestial objects, waiting to be unlocked. This is where spectroscopy comes in, a powerful tool that transforms starlight into a cosmic fingerprint, revealing the universe's deepest mysteries. By breaking down light into its component colors, astronomers can read the unique signatures of elements and molecules, uncovering the stories written in the very fabric of the cosmos. One of the most remarkable achievements of spectroscopy was the discovery of helium, an element found on Earth but first identified in the Sun. In the mid-19th century, scientists analyzing the Sun's spectrum noticed a series of bright yellow lines that didn't match any known element. They named this new element helium after Helios, the Greek god of the sun. It was a groundbreaking moment, proving that the same elements found on Earth exist throughout the universe. Spectroscopy has since become a cornerstone of astronomy, enabling us to study the chemical makeup of stars, the atmospheres of distant planets, and even the gas clouds where new stars are born. But spectroscopy doesn't just tell us what's out there, it also reveals how the universe is moving. One of the most profound discoveries in cosmology came from studying the light of distant galaxies. When astronomers examined their spectra, they noticed something peculiar. The light was shifted toward the red end of the spectrum. This phenomenon, known as redshift, occurs because the universe is expanding, stretching the wavelengths of light as it travels through space. The greater the redshift, the faster the galaxy is moving away from us. This discovery, first made in the early 20th century, provided the first direct evidence of the universe's expansion, laying the foundation for our modern understanding of cosmology. Redshift isn't just a curiosity, it's a vital tool for measuring the distances to faraway objects. By comparing the redshift of a galaxy to its apparent brightness, astronomers can calculate how far away it is and how long its light has been traveling to reach us. This technique has allowed us to map the large-scale structure of the universe, from nearby galaxies to the most distant quasars, billions of light-years away. It's a testament to the power of spectroscopy, transforming starlight into a cosmic ruler that helps us measure the vastness of space and time. Yet, spectroscopy is only part of the story. To fully understand the universe, astronomers also rely on computer simulations, which recreate the complex processes that shape galaxies, stars, and planets. These simulations, powered by some of the most advanced supercomputers in the world, allow scientists to test theories and explore scenarios that would be impossible to observe directly. From the birth of the first stars to the collisions of galaxies, simulations bring the cosmos to life, offering insights that complement the data gathered through spectroscopy and other observational techniques. Together, these tools form a powerful partnership, helping us piece together the grand narrative of the universe and our place within it. As we continue to refine these techniques, each discovery brings us closer to understanding the cosmos on a deeper level. Spectroscopy reminds us that the universe is not just a collection of distant lights, it's a dynamic, ever-changing tapestry, woven together by the forces of nature and illuminated by the stories written in starlight. And as we'll explore next, the combination of observation and simulation is opening doors to new frontiers, revealing the universe in ways we've only begun to imagine. To truly understand the universe, we need more than just telescopes and spectrometers. We need the power of supercomputers. These technological marvels allow us to recreate the cosmos in digital form, simulating the birth of stars, the collisions of galaxies, and the intricate growth of the cosmic web. By building virtual universes, scientists can test theories, explore scenarios that would take billions of years to unfold in real time, and uncover the hidden processes that shape everything we see in the night sky. It's like having a time machine for the cosmos, one that lets us rewind and fast forward through the universe's history with incredible precision. One of the most ambitious projects in this field is the Millennium Simulation, a groundbreaking effort to model the universe's evolution over billions of years. Using a supercomputer, scientists recreated a virtual cosmos, starting from just moments after the Big Bang and following the growth of galaxies, the formation of dark matter halos, and the intricate weaving of the cosmic web. The simulation tracked the movements of billions of particles, each representing a clump of matter, as they were shaped by gravity and dark energy. The result was a stunningly detailed map of the universe's structure, revealing how tiny fluctuations in the early cosmos grew into the vast, interconnected network of galaxies we see today. It's a testament to how far computational power has come and how much it can teach us about the universe, but simulating the cosmos isn't without its challenges. Take star formation, for example. Stars are born in dense clouds of gas and dust, where gravity pulls material together until it ignites into a fiery ball. Sounds simple, right? The reality is far more complex. These clouds are turbulent, chaotic environments shaped by magnetic fields, radiation, and the explosions of nearby stars. Modeling every detail requires staggering amounts of computational power and sophisticated algorithms. Even then, simulations can only approximate the intricate dance of forces at play. Yet, despite these hurdles, scientists have made incredible strides, using simulations to study how stars form, how they cluster together, and how they influence their surroundings. Galaxy collisions, too, present a fascinating challenge. When two galaxies collide, the result is a cosmic spectacle. Stars are flung into new orbits, gas clouds are compressed, and supermassive black holes at their centers can merge, releasing bursts of energy. Simulating these events requires not just raw computing power, but also an understanding of the physics at play, from gravity to gas dynamics. These simulations have revealed how collisions can trigger bursts of star formation, reshape galaxies into new forms, and even create the conditions for supermassive black holes to grow. They've also given us a front-row seat to some of the most dramatic events in the universe, helping us piece together the story of how galaxies evolve over time. Perhaps the most awe-inspiring aspect of these simulations is their ability to trace the growth of the cosmic web. By modeling the distribution of dark matter and gas, scientists can watch as gravity pulls matter into dense filaments, forming the backbone of the universe. These filaments intersect at nodes where galaxy clusters form, creating the intricate structure we see today. Simulations have shown how the cosmic web evolves over billions of years, shaped by the interplay of gravity, dark matter, and dark energy. They've also helped us understand the role of feedback processes like supernova explosions and black hole activity in regulating star formation and shaping galaxies. As we continue to refine these simulations, they're becoming more than just tools for understanding the past. They're helping us predict the future. By tweaking the parameters, scientists can explore different scenarios, from the fate of individual galaxies to the ultimate destiny of the universe itself. These virtual experiments complement observations from telescopes, filling in gaps and revealing processes that are too slow or too distant to study directly. Together, simulations and observations are painting an ever clearer picture of the cosmos, one that captures both its beauty and its complexity. But the story doesn't end here. As powerful as simulations are, they're just one piece of the puzzle. The next frontier in our exploration of the universe lies in combining different ways of observing it, a field known as multi-messenger astronomy. By studying not just light, but also gravitational waves, neutrinos, and cosmic rays, we can gain a more complete understanding of the universe's most extreme events. This approach has already transformed our understanding of phenomena like neutron-star collisions and black hole mergers, and it promises to unlock even more secrets in the years to come. As we'll explore next, multi-messenger astronomy is opening a new chapter in our quest to understand the cosmos, one that brings us closer than ever to unraveling its deepest mysteries. The universe doesn't just speak to us through light, it whispers in gravitational waves, hums in neutrinos, and even sends ripples across the cosmic fabric itself. For centuries, astronomy relied almost entirely on what we could see, from the twinkle of stars to the glow of distant galaxies. But now, we're learning to listen to the cosmos in entirely new ways. This is the dawn of multi-messenger astronomy, a revolutionary approach that combines observations of light, gravitational waves, and neutrinos to paint a fuller picture of the universe's most dramatic events. It's like turning on a new set of senses, allowing us to experience the cosmos in ways we never thought possible. One of the most groundbreaking discoveries in this field came in 2015, when scientists detected gravitational waves for the first time. These ripples in space-time, predicted by Einstein a century earlier, were created by the collision of two black holes over 1 billion light-years away. The detection was a triumph of human ingenuity, made possible by the Laser Interferometer Gravitational Wave Observatory, or LIGO. Suddenly, we weren't just observing the universe, we were feeling its tremors. Gravitational waves opened a new window into the cosmos, revealing events that were completely invisible to traditional telescopes. From the mergers of black holes to the collisions of neutron stars, these waves carry information about the most violent and energetic processes in the universe. But gravitational waves are just one piece of the puzzle. Neutrinos, often called ghost particles, are another key messenger. These tiny, nearly massless particles travel through the universe at nearly the speed of light, passing through matter as if it weren't even there. While they are incredibly difficult to detect, neutrinos carry crucial information about the inner workings of stars, supernovae, and even the cores of galaxies. When combined with gravitational waves and light, neutrinos provide a more complete picture of cosmic events, like pieces of a puzzle coming together to reveal a hidden image. Take the collision of two neutron stars in 2017, for example. This event, detected by both LIGO and traditional telescopes, marked the first time astronomers observed the same phenomenon in gravitational waves and light. The result was extraordinary. Not only did we witness the birth of a black hole, but we also saw the creation of heavy elements like gold and platinum, forged in the fiery aftermath of the collision. It was a stunning demonstration of how multi-messenger astronomy can deepen our understanding of the universe, revealing processes that would otherwise remain hidden. What makes this approach so powerful is its ability to bring together different fields of science. Gravitational waves, neutrinos, and light each tell a different part of the story, offering unique insights that complement one another. By combining these observations, we can study the universe in unprecedented detail, from the formation of black holes to the behavior of matter under extreme conditions. It's an interdisciplinary effort, uniting astronomers, physicists, and engineers in a shared quest to unravel the cosmos's deepest mysteries. As we continue to refine these techniques, the potential for discovery is immense. Multi-messenger astronomy could help us understand the nature of dark matter, probe the interiors of neutron stars, and even uncover the origins of the universe itself. But its implications extend beyond pure science. By studying the cosmos in all its forms, we're also taking the first steps toward answering one of humanity's oldest questions: are we alone in the universe? This question, deeply tied to the study of galaxies and the conditions that make life possible, will guide our next chapter as we turn our gaze outward in search of other worlds and perhaps other civilizations. The search for life beyond Earth is one of the most profound and enduring questions in science. Are we alone in the universe, or is life a cosmic phenomenon scattered across countless worlds? To answer this, we must first understand what makes life possible. Water, often called the universal solvent, is essential for life as we know it. Its unique properties allow it to dissolve nutrients, transport chemicals, and facilitate the complex reactions that sustain living organisms. But water alone isn't enough. Life also requires a source of energy, a stable environment, and the presence of organic molecules, carbon-based compounds that form the building blocks of everything from proteins to DNA. Together, these ingredients create the recipe for life, a recipe that might not be unique to Earth. As we peer into the cosmos, we've discovered that these ingredients are surprisingly common. Exoplanets, worlds orbiting stars beyond our solar system, have opened a new frontier in the search for life. Some of these planets lie within their star's habitable zone, a region where temperatures are just right for liquid water to exist. Others, like Jupiter's moon Europa or Saturn's moon Enceladus, hide vast oceans beneath their icy surfaces, heated by the gravitational pull of their parent planets. These discoveries have shifted our perspective, showing that life could thrive in environments we once thought inhospitable. The universe, it seems, is teeming with possibilities. The James Webb Space Telescope is at the forefront of this search, equipped with the tools to detect biosignatures, chemical traces that could indicate the presence of life. By analyzing the atmospheres of distant exoplanets, Webb can identify gases like oxygen, methane, or even complex organic molecules. Imagine the moment when we detect a planet with an atmosphere rich in oxygen, a gas that, on Earth, is produced by living organisms. Such a discovery would be a monumental step forward, offering the tantalizing possibility that life exists elsewhere in the cosmos. But even if we find these signs, the challenge remains: how do we confirm that they truly indicate life? This brings us to a profound and puzzling question. If the universe is so vast and the conditions for life so widespread, why haven't we found evidence of extraterrestrial civilizations? This dilemma is known as the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everyone?" The paradox highlights the tension between the high probability of life existing elsewhere and the lack of observable evidence for it. With billions of stars in our galaxy alone, many of which host planets, it seems almost inevitable that intelligent life should have arisen somewhere. Yet the silence of the cosmos is deafening. Possible explanations for the Fermi paradox range from the practical to the philosophical. Perhaps intelligent civilizations are rare, or their lifespans are too short to overlap with ours. Maybe they communicate in ways we can't detect, or they've chosen to remain hidden. Some even suggest that advanced civilizations inevitably destroy themselves, a sobering reminder of the challenges we face as a species. Whatever the answer, the Fermi paradox forces us to confront the enormity of the universe and our place within it. It's a question that doesn't just challenge our scientific understanding, it challenges us to think deeply about who we are and what our future might hold. As we continue to explore, the search for extraterrestrial life remains one of the most exciting and humbling endeavors in science. Every new discovery brings us closer to answering one of humanity's oldest questions: are we alone? Whether we find microbial life on a distant moon or detect the faint signals of a distant civilization, the implications will be profound. It would reshape our understanding of the universe, our place within it, and the very nature of life itself. The search is far from over, and the answers, whatever they may be, promise to reveal a universe far more wondrous than we've ever imagined. The Fermi paradox isn't just a scientific question, it's a cosmic riddle that challenges our assumptions about life and the universe itself. With billions of stars in our galaxy alone, many of which host planets in their habitable zones, it seems almost inevitable that intelligent life should exist somewhere out there. Yet, as Enrico Fermi famously asked, "Where is everyone?" the silence of the cosmos is both puzzling and profound. leaving us to wonder why we haven't found any signs of extraterrestrial civilizations, despite the sheer scale of the universe. One possible explanation lies in the rarity of intelligent life. While the universe may be teeming with planets, the conditions needed to sustain life, let alone nurture intelligence, might be extraordinarily rare. Life on Earth took billions of years to evolve into complex organisms, and even then, intelligence emerged only recently in the grand timeline of our planet. Perhaps the emergence of civilizations is a cosmic fluke, a one-in-a-billion occurrence that makes humanity unique in the galaxy, or even the universe. Another possibility is the immense challenge of interstellar communication. The distances between stars are so vast that even light, the fastest thing in the universe, takes years to travel from one star to the next. For civilizations separated by light years, exchanging messages could take centuries or longer. By the time a signal reaches its destination, the civilization that sent it might no longer exist. This great silence could simply be a matter of timing. Our signals and theirs may be passing each other in the void, never to meet. But there's a darker side to the Fermi paradox, one that forces us to confront the fragility of intelligent life. Some scientists suggest that advanced civilizations inevitably self-destruct, whether through war, environmental collapse, or technological catastrophe. If this is true, the silence of the cosmos might be a sobering reminder of the challenges we face as a species. It's a scenario that underscores the importance of safeguarding our planet and using our knowledge responsibly, not just for our survival, but for the survival of any civilization that might follow in our footsteps. Despite these uncertainties, the Fermi paradox isn't just a source of frustration, it's a call to action. It reminds us that the universe is vast, mysterious, and full of possibilities. Every unanswered question is an invitation to explore, to push the boundaries of our knowledge and search for answers among the stars. And while we may not have found extraterrestrial civilizations yet, the search itself has transformed our understanding of the cosmos, revealing the incredible diversity of planets, stars, and galaxies that fill the night sky. This relentless curiosity, this drive to explore and understand, is what sets humanity apart. From the first time our ancestors looked up at the stars to the modern era of space telescopes and interplanetary probes, our quest to unravel the mysteries of the universe has shaped who we are. It's a journey that transcends science, touching on philosophy, art, and the very essence of what it means to be human. And as we continue to explore, we're not just searching for answers, we're discovering the boundless potential of our own species. The next chapter in this journey lies in the stars themselves, where the tools of modern astronomy are opening new doors to discovery. From the James Webb Space Telescope to the search for biosignatures on distant worlds, we're uncovering clues that could one day solve the Fermi paradox, or perhaps reveal that the answer was within us all along. Whatever we find, the pursuit of knowledge will continue to light our way, guiding us through the vast and wondrous cosmos we call home. Humanity's journey into the cosmos is more than a series of missions. It's a testament to our insatiable curiosity and unyielding desire to explore the unknown. From the moment we first gazed at the stars, we've dreamed of reaching beyond our world, driven by a fundamental question: what lies beyond? This quest has taken us from the first tentative steps on the moon to the farthest reaches of our solar system. Each milestone, a reminder of what we can achieve when we dare to push the boundaries of possibility. The Apollo moon landings stand as one of humanity's greatest achievements, not just for the technological triumph they represented, but for the way they transformed our perspective. When Neil Armstrong set foot on the lunar surface in 1969, he carried with him the hopes and dreams of an entire planet. That single step was a giant leap for humanity, proving that with ingenuity, determination, and collaboration, we could achieve the seemingly impossible. The images of Earth rising over the lunar horizon, a fragile blue marble suspended in the void, reshaped how we see our place in the universe, emphasizing both our insignificance and our extraordinary potential. But the exploration didn't stop there. The Voyager probes, launched in the late 1970s, carried humanity's curiosity even further. These intrepid spacecraft ventured beyond the outer planets, capturing breathtaking images of Jupiter's swirling storms, Saturn's majestic rings, and the icy moons that might hide oceans beneath their surfaces. Today, Voyager 1 and 2 continue their journey into interstellar space, carrying with them the golden records, a message to any future civilizations that might one day find them. These records, etched with sounds and images from Earth, are a reminder that exploration isn't just about discovery, it's about connection, a way of reaching out to the cosmos and saying, "We were here." What makes these missions even more remarkable is the spirit of international collaboration that drives them. Space exploration has always been a global endeavor, with nations coming together to share knowledge, resources, and expertise. The International Space Station, a symbol of cooperation in orbit, has hosted astronauts from over 20 countries, working side by side to conduct experiments that benefit all of humanity. This spirit of unity reminds us that, despite our differences, we are all explorers at heart, bound by a shared curiosity about the universe and our place within it. As we look to the future, the possibilities are limitless. Missions like NASA's Artemis program aim to return humans to the moon, this time to stay, while projects like the European Space Agency's JUICE mission will explore the icy moons of Jupiter, searching for signs of life. The James Webb Space Telescope continues to peer into the distant past, revealing the earliest galaxies and shedding light on the origins of the universe. Each mission brings us closer to answering the big questions. How did it all begin? Are we alone? And what lies beyond the horizon of our current understanding? This relentless pursuit of knowledge isn't just about answering questions. It's about uncovering new mysteries, sparking new ideas, and inspiring future generations to dream bigger. It's a reminder that exploration is more than a journey through space. It's a journey through time. By studying the light from distant stars and galaxies, we're essentially looking back in time, witnessing the universe as it was billions of years ago. This connection between exploration and time, between the past, present, and future, brings us to an intriguing concept: the idea of time travel, not as science fiction, but as a lens through which we can better understand the history and evolution of the cosmos. What if the key to unraveling the universe's greatest secrets lies not just in traveling through space, but in bending the very fabric of time itself? Imagine if you could step into a time machine and witness the birth of the first stars or the collision of ancient galaxies. While we may not have a machine that bends time itself, astronomy gives us the next best thing: a cosmic time machine. Every time we look at the night sky, we're not just seeing distant stars and galaxies, we're peering into the past. Light from these celestial objects has traveled across the vastness of space, sometimes for billions of years, before finally reaching us. This means that when we observe a galaxy 10 billion light-years away, we're seeing it as it was 10 billion years ago, a snapshot of the universe in its youth. This phenomenon isn't just a neat trick of physics, it's a powerful tool for understanding the evolution of the cosmos. By studying light from galaxies at different distances, astronomers can piece together a timeline of the universe's history. For example, the Hubble and James Webb Space Telescopes have captured images of galaxies that existed when the universe was just a fraction of its current age. These ancient galaxies are smaller, more chaotic, and bursting with star formation, offering a glimpse into a time when the universe was a very different place. It's like flipping through a cosmic photo album, watching the universe grow and mature over billions of years. But this cosmic time machine doesn't just show us the past, it also helps us understand the forces that shaped the universe into what it is today. Take dark matter, for instance. While we can't see it directly, its gravitational influence is written into the structure of the cosmos. By observing how galaxies cluster and move, scientists can map the distribution of dark matter, revealing the invisible scaffolding that holds the universe together. These observations, combined with our ability to look back in time, allow us to trace how dark matter has shaped the growth of galaxies and the large-scale structure of the cosmos. The implications of this are profound. By studying the universe at different stages of its evolution, we can test theories about how stars form, how galaxies grow, and how dark matter and dark energy influence the cosmos. It's a bit like solving a cosmic puzzle, where each piece of light from the past helps us build a clearer picture of the universe's history and its future. As we continue to explore these mysteries, we're reminded that the universe isn't just a static backdrop. It's a dynamic, ever-changing tapestry, woven together by the forces of nature and illuminated by the stories written in starlight. And as we delve deeper into these questions, one thing becomes clear: the universe is far more interconnected than we ever imagined. From the tiniest fluctuations in the early cosmos to the vast, shimmering web of galaxies that spans the universe, every piece of the puzzle is linked by the invisible threads of dark matter and the relentless expansion driven by dark energy. These forces, though mysterious, are the architects of the cosmos, shaping its structure and guiding its evolution. As we'll explore next, understanding these hidden elements is key to unlocking the universe's deepest secrets, and perhaps even its ultimate fate. The universe, as we see it, stars, galaxies, and glowing nebulae, is just the tip of the cosmic iceberg. Beneath the surface lies a hidden realm, one that shapes everything we observe yet remains utterly invisible. This is the realm of dark matter, a mysterious substance that makes up roughly 27% of the universe's total mass and energy. Unlike ordinary matter, dark matter doesn't emit, absorb, or reflect light, making it completely undetectable by traditional telescopes. Yet its presence is undeniable, revealed through the subtle but profound effects it has on the cosmos. The story of dark matter begins with the motion of galaxies. In the 1930s, astronomer Fritz Zwicky noticed something strange while studying galaxy clusters. The galaxies within these clusters were moving so fast that, according to the laws of gravity, they should have flown apart. Yet they remained bound together, as if held by an invisible hand. Zwicky proposed the existence of unseen matter, which he called dark matter, to explain this phenomenon. Decades later, Vera Rubin's observations of spiral galaxies confirmed this idea. She found that stars at the edges of galaxies were orbiting just as fast as those near the center, a behavior that defied expectations unless some unseen mass was pulling on them. These discoveries laid the groundwork for our modern understanding of dark matter, a substance that doesn't interact with light but exerts a powerful gravitational influence. But how do we study something we can't see? The key lies in its gravitational effects. Dark matter's pull shapes the large-scale structure of the universe, bending the paths of light from distant galaxies in a phenomenon known as gravitational lensing. By mapping these distortions, astronomers can create detailed maps of dark matter's distribution, revealing the invisible scaffolding that holds galaxies and galaxy clusters together. These maps show that dark matter isn't spread evenly. It forms a cosmic web, with dense filaments connecting galaxies and vast voids in between. It's a hidden architecture, one that has guided the growth of the universe since its earliest moments. Despite its elusive nature, scientists are determined to uncover the secrets of dark matter. Experiments around the world are searching for dark matter particles, using ultra-sensitive detectors buried deep underground to shield them from cosmic noise. One leading candidate is the WIMP, or weakly interacting massive particle, which could interact with ordinary matter only through gravity and the weak nuclear force. Other theories propose lighter particles, like actions, or even massive black holes formed in the early universe. While no definitive detection has been made yet, each experiment brings us closer to understanding what dark matter truly is. The implications of discovering dark matter are immense. It could revolutionize our understanding of physics, offering clues about the nature of the universe's missing mass and even the forces that govern it. For cosmologists, it's a missing piece of the puzzle, one that could help explain how galaxies formed and why the universe looks the way it does today. But dark matter isn't the only mystery shaping the cosmos. Its influence is intertwined with another enigmatic force, dark energy, and the story of the universe's evolution begins even earlier, in a fleeting moment known as cosmic inflation. Cosmic inflation is the theory that, just after the Big Bang, the universe underwent an exponential expansion, stretching from a tiny speck to something unimaginably large in a fraction of a second. This rapid growth would have smoothed out the universe, creating the conditions for galaxies and galaxy clusters to form later, but it also left behind subtle ripples in space-time, imprints that we can still detect today in the cosmic microwave background. These ripples, tiny variations in temperature and density, are the seeds from which galaxies, stars, and even dark matter structures grew. Inflation isn't just a theory, it's a framework that helps explain why the universe looks the way it does, from the largest scales to the smallest. Together, dark matter and cosmic inflation form the foundation of our modern understanding of the cosmos. They are the invisible forces that shape the universe from its earliest moments, guiding the formation of galaxies, stars, and planets. Yet, for all we've learned, these mysteries remain unsolved, reminding us that the universe is far more complex and far more wondrous than we ever imagined. As we continue to explore, each discovery brings us closer to unraveling the secrets of the cosmos, revealing a universe that is as strange as it is beautiful. To understand the universe's earliest moments, we must venture back to a time when everything we know, every star, galaxy, and atom, was compressed into an unimaginably tiny point. This is the story of the Big Bang, the explosive event that marked the birth of our cosmos. But the Big Bang wasn't just a single moment. It was the beginning of a series of extraordinary events, one of the most pivotal being cosmic inflation. This theory suggests that in the first fraction of a second after the Big Bang, the universe underwent a rapid, exponential expansion, stretching from a speck smaller than an atom to something far larger than our observable universe today. It's a concept that might sound like science fiction, but it's grounded in some of the most compelling evidence we have about the cosmos. One of the key pieces of evidence for cosmic inflation lies in the cosmic microwave background, or CMB. This faint afterglow of the Big Bang, discovered in the 1960s, is like a snapshot of the universe when it was just 380,000 years old. What's remarkable about the CMB is its uniformity. No matter where we look in the sky, the temperature of this ancient light is almost exactly the same, varying by less than 1 part in 100,000. This uniformity is a mystery because without inflation, regions of the universe that are now far apart would have been too distant to ever interact and reach the same temperature. Inflation solves this puzzle by suggesting that these regions were once close together, allowing them to equalize before being stretched apart by the rapid expansion. It's like taking a single drop of ink in a glass of water, stir it well, and the entire glass becomes uniformly colored, but the CMB isn't just uniform, it also contains tiny fluctuations, slight variations in temperature that act as cosmic fingerprints. These fluctuations are the seeds from which galaxies and galaxy clusters eventually grew. Inflation predicts that these variations should follow a specific pattern, and observations from satellites like the Planck mission have confirmed this with stunning precision. The match between theory and observation is so strong that it's one of the most compelling arguments for cosmic inflation. These fluctuations aren't random, they're a direct result of quantum processes that occurred during inflation, magnified by the rapid expansion of the universe. In a sense, the largest structures in the cosmos, galaxies, clusters, and the cosmic web itself, are the legacy of quantum mechanics playing out on a cosmic scale. Cosmic inflation also helps explain another puzzling feature of the universe, its flatness. If you were to measure the angles of a triangle drawn on the surface of the universe, they would add up to exactly 180 degrees, just as they would on a flat piece of paper. This flatness is a direct consequence of inflation, which smoothed out any curvature in the early universe, much like blowing up a balloon flattens its surface. Without inflation, this level of flatness would be incredibly unlikely, almost like balancing a pencil on its tip and expecting it to stay upright indefinitely. Yet inflation isn't just about solving puzzles, it's about opening new ones. For example, what caused inflation to start, and why did it stop? Some theories suggest that inflation was driven by a mysterious field of energy, often called the inflaton field, which permeated the early universe. When this field decayed, it released energy that heated the universe, marking the end of inflation and the beginning of the hot, dense state we associate with the Big Bang. But the details remain elusive, leaving scientists to grapple with questions about the nature of this field and the forces that governed it. The cosmic microwave background is more than just a relic of the past. It's a treasure trove of information about the universe's origins and evolution. By studying its patterns, scientists can test theories about inflation, dark matter, and even the ultimate fate of the cosmos. It's a reminder that the universe is not just a static backdrop, but a dynamic, ever-changing entity, shaped by forces that are still being uncovered. And as we continue to explore these mysteries, each discovery brings us closer to understanding the grand story of the cosmos, a story that began with a single, explosive moment and continues to unfold with every passing second. The cosmic microwave background, or CMB, is like a time capsule from the universe's infancy, a faint glow that has traveled across the cosmos for over 13 billion years to reach us. It's the oldest light we can observe, a relic from a time when the universe was just 380,000 years old. Back then, the cosmos was a hot, dense soup of particles, so thick that light couldn't travel far before being scattered. But as the universe expanded and cooled, electrons and protons combined to form atoms, allowing light to break free. That first burst of light has been stretching and cooling ever since, and today we detect it as microwave radiation, a whisper from the dawn of time. What makes the CMB so extraordinary is its uniformity. No matter where we look in the sky, the temperature of this ancient light is almost identical, varying by less than 1 part in 100,000. This uniformity tells us that the early universe was remarkably smooth, a surprising finding that puzzled scientists for decades. How could regions of the universe that are now billions of light years apart have been so perfectly synchronized? The answer lies in cosmic inflation, the rapid expansion that occurred just after the Big Bang. Inflation stretched the universe to an unimaginable size, smoothing out irregularities and setting the stage for the cosmos we see today. But the CMB isn't perfectly uniform. Tiny fluctuations in temperature, no larger than a few millionths of a degree, are scattered throughout this ancient light. These fluctuations are the cosmic equivalent of fingerprints, revealing the seeds of future galaxies and galaxy clusters. Where the CMB is slightly warmer, matter was slightly denser, and over billions of years, gravity amplified these differences, pulling matter together to form the vast structures we see today. It's a humbling thought. The galaxies we observe, the stars that light up the night sky, and even the planets we call home all trace their origins to these faint ripples in the early universe. Mapping these fluctuations with precision has been one of the great achievements of modern cosmology. Missions like the Planck satellite have scanned the entire sky, measuring the CMB with incredible detail. Planck's observations have confirmed the predictions of cosmic inflation, revealing patterns in the CMB that match our theoretical models with stunning accuracy. These maps don't just tell us about the early universe, they also provide clues about its composition. By analyzing the CMB, scientists have determined that ordinary matter, the stuff that makes up stars, planets, and us, makes up just 5% of the universe. The rest is dark matter and dark energy, two mysterious components that continue to shape the cosmos. The CMB also offers glimpses of particles that were present in the early universe, but are now incredibly difficult to detect. For instance, the faint polarization patterns in the CMB hint at the presence of neutrinos, ghostly particles that barely interact with matter. These neutrinos, produced in staggering numbers during the Big Bang, have been streaming through the universe ever since, leaving behind subtle imprints in the CMB. Studying these imprints could shed light on the properties of neutrinos and their role in the universe's evolution, opening a new window into the hidden world of particle physics. As we continue to unravel the secrets of the cosmic microwave background, it's clear that this ancient light holds more than just the story of the universe's past. It's also a roadmap to its future. The fluctuations we see today set the stage for the galaxies, stars, and planets that would form billions of years later, and they continue to shape the cosmos as it evolves. The CMB reminds us that the universe is a dynamic, ever-changing entity, filled with mysteries that challenge our understanding and inspire us to explore further. And as we'll see next, the story of the cosmos doesn't end with the CMB. It's just the beginning of a journey that takes us deeper into the fabric of space and time. Among the countless particles that emerged from the Big Bang, one of the most elusive and fascinating is the neutrino. These ghostly subatomic particles, nearly massless and with no electric charge, are so stealthy that they can pass through entire planets without ever interacting with matter. Yet, despite their elusive nature, neutrinos played a crucial role in shaping the early universe. Produced in staggering numbers during the first seconds of the cosmos, they carried away energy and momentum, influencing the delicate balance of forces that govern the universe's infancy. Without neutrinos, the universe as we know it might have looked very different. In those early moments, the universe was a seething cauldron of energy, with temperatures so high that particles and antiparticles were constantly being created and annihilated. Neutrinos were among the first particles to form, pouring out in vast quantities as the universe expanded and cooled. Unlike other particles, neutrinos rarely interact with matter, allowing them to stream freely through the cosmos. This property makes them incredibly difficult to detect, but it also means they carry pristine information about the conditions of the early universe, untouched by the passage of time. One of the most intriguing ways neutrinos shaped the cosmos is through their influence on the formation of the first stars and galaxies. As the universe expanded, the pull of gravity began to gather matter into dense clouds, eventually igniting the first stars. But neutrinos, with their ability to travel vast distances without being absorbed, helped regulate this process. They carried energy away from dense regions, cooling them down and allowing gravity to take hold more effectively. In a sense, neutrinos were the silent architects of the universe's first structures, their subtle influence guiding the growth of galaxies and stars. Today, scientists are working tirelessly to detect these cosmic neutrinos, hoping to uncover new insights into the universe's history. Experiments like the Ice Cube Neutrino Observatory, buried deep in the Antarctic ice, are designed to catch the rare moments when a neutrino collides with an atom, producing a faint flash of light. By studying these interactions, researchers can trace the neutrinos back to their sources, whether they are from the distant reaches of the cosmos or the fiery hearts of supernova. Each detection is a window into the universe's earliest moments, offering clues about the forces that shaped its evolution. But neutrinos aren't the only cosmic messengers traveling through the universe. Another, even more energetic phenomenon is at work: cosmic rays. These high-energy particles, often protons or atomic nuclei, zip through space at nearly the speed of light, colliding with atoms in Earth's atmosphere and creating showers of secondary particles. While they're not as stealthy as neutrinos, cosmic rays are equally mysterious, carrying energy from some of the most violent events in the universe, like supernova, black holes, and even the remnants of the Big Bang itself. Together, neutrinos and cosmic rays form a cosmic symphony, each playing a unique role in the story of the universe, a story that continues to unfold with every new discovery. Cosmic rays are like the universe's high-speed messengers, zipping through space at nearly the speed of light. These particles, often protons or atomic nuclei, carry immense energy, so much so that they can collide with atoms in Earth's atmosphere, creating cascades of secondary particles that rain down on our planet. But where do these cosmic rays come from, and what can they tell us about the most extreme environments in the cosmos? The answers lie in some of the most violent and energetic events imaginable, from the explosive deaths of massive stars to the supermassive black holes at the hearts of distant galaxies. One of the primary sources of cosmic rays is supernova, the spectacular explosions that mark the end of a star's life. When a massive star exhausts its fuel, its core collapses, triggering a shockwave that blasts the star's outer layers into space. This explosion doesn't just create stunning nebulae, it also accelerates particles to incredible speeds, sending them hurtling across the cosmos as cosmic rays. These particles can travel for millions, or even billions, of years, carrying with them the energy of their violent origins, but supernova aren't the only source. Active galactic nuclei, powered by supermassive black holes, also produce cosmic rays. As matter falls into these black holes, it heats up and emits intense radiation, while powerful magnetic fields can fling particles outward at nearly the speed of light. The effects of cosmic rays extend far beyond their points of origin. As they travel through space, they interact with the gas and dust that fill the interstellar medium, ionizing atoms and molecules. This ionization plays a crucial role in shaping the chemistry of galaxies, influencing how stars form and how gas clouds evolve. In some cases, cosmic rays can even trigger star formation by compressing gas clouds, setting off a chain reaction that leads to the birth of new stars. They're not just passive travelers, they're active participants in the cosmic drama, shaping the universe on both small and large scales. Studying cosmic rays, however, is no easy task. Because they're charged particles, their paths are bent by magnetic fields as they travel through space, making it nearly impossible to trace them back to their sources. To overcome this challenge, scientists use a combination of ground-based detectors and space-based observatories. Instruments like the Pierre Auger Observatory in Argentina and the High-Altitude Water Cherenkov Observatory in Mexico are designed to detect the showers of secondary particles created when cosmic rays hit Earth's atmosphere. Meanwhile, space missions like the Alpha Magnetic Spectrometer aboard the International Space Station measure cosmic rays directly, helping us understand their composition and energy. What makes cosmic rays so fascinating isn't just their origins or their effects, it's the potential they hold for unlocking new cosmic mysteries. Some of the most energetic cosmic rays, known as ultra-high-energy cosmic rays, carry as much energy as a fast-pitched baseball packed into a single particle. How particles can reach such extreme energies remains one of the great unsolved questions in astrophysics. Could they come from even more exotic sources, like the decay of massive particles left over from the Big Bang, or are they the result of processes we haven't yet discovered? Each detection brings us closer to answering these questions, offering a glimpse into the universe's most extreme environments. But cosmic rays don't travel alone. Their journeys are shaped by another invisible force, magnetic fields. These fields, woven through galaxies and the vast spaces between them, influence not only the paths of cosmic rays, but also the structure and evolution of the cosmos itself. From the birth of stars to the dynamics of galaxy clusters, magnetic fields are a hidden yet powerful force, quietly shaping the universe in ways we're only beginning to understand. Their role in the cosmic story is as profound as it is subtle, and it's here that our journey will take us next. Magnetic fields are the invisible threads that weave through the cosmos, shaping the behavior of stars, galaxies, and even the vast spaces between them. Though we can't see them directly, their influence is everywhere, from the swirling arms of spiral galaxies to the fiery hearts of stars. These fields are created by the motion of charged particles, like electrons and protons, which generate electric currents. As these currents flow, they produce magnetic fields, turning the universe into a dynamic tapestry of forces that guide the movement of matter and energy. In stars, magnetic fields play a crucial role in regulating their activity. Take our Sun, for example. Its magnetic field is responsible for the sunspots, solar flares, and coronal mass ejections that occasionally disrupt communications and power grids on Earth. These phenomena occur when the Sun's magnetic field lines become twisted and tangled, releasing bursts of energy that ripple through the solar system. But the Sun is just one star among billions. In other stars, particularly those with strong magnetic fields, These forces can influence everything from their rotation rates to the flow of material on their surfaces. In some cases, magnetic fields can even shape the remnants of dying stars, creating the intricate patterns seen in planetary nebulae. Galaxies, too, are shaped by magnetic fields. Spiral galaxies, like our Milky Way, are threaded with magnetic fields that align with their swirling arms. These fields influence how gas and dust move within galaxies, guiding the formation of new stars and even affecting the trajectories of cosmic rays. In regions where star formation is intense, magnetic fields can compress gas clouds, triggering the birth of new stars, but they can also create turbulence, slowing down star formation in other areas. This delicate balance between creation and restraint is one of the ways magnetic fields help regulate the life cycle of galaxies. Beyond individual galaxies, magnetic fields extend into the intergalactic medium, the vast, nearly empty spaces between galaxies. Here, they play a role in shaping the large-scale structure of the universe. Magnetic fields can influence how gas flows into galaxy clusters, the largest structures in the cosmos, and even affect the behavior of cosmic rays as they travel through these regions. These fields are thought to be amplified by the motion of gas and the collisions of galaxies, creating a complex network that connects the universe on the grandest scales. Understanding these magnetic fields is no easy task. Because they're invisible, scientists rely on indirect methods to study them. Observations of polarized light that vibrates in a specific direction reveal the orientation of magnetic fields in stars and galaxies. Meanwhile, computer simulations allow researchers to model how these fields evolve over time, from the birth of stars to the merging of galaxies. These simulations provide a virtual laboratory where scientists can test theories and explore scenarios that would be impossible to observe directly, offering insights into the intricate interplay between magnetic fields and cosmic structures. As we continue to unravel the mysteries of magnetic fields, one thing becomes clear: they are a fundamental force in the universe, shaping its evolution in ways we're only beginning to understand. Their influence extends from the smallest scales, where they guide the birth of stars, to the largest, where they connect galaxies across the cosmos. And as we turn our attention to another hidden element of the universe, cosmic dust, we'll see how even the tiniest particles play a role in the grand story of the cosmos, from the formation of stars to the creation of planets like our own. Cosmic dust may seem like an insignificant afterthought in the grand scheme of the universe, but these tiny particles are the unsung heroes of star and planet formation. Composed of carbon, silicates, and other minerals, these microscopic grains are scattered throughout space, often invisible to the naked eye, yet their role is anything but small. Cosmic dust acts as a cosmic glue, gathering in vast clouds that become the birthplaces of stars and planets. Without these seemingly humble particles, the universe as we know it might never have taken shape. The journey begins in the cold, dark regions of space, where gas and dust gather into dense clouds. These clouds, often spanning light years, are the nurseries of the cosmos. But for stars to form, something has to trigger the collapse of these clouds. This is where cosmic dust comes in. Dust grains, though tiny, play a crucial role in cooling the gas within these clouds. As gas molecules collide with the dust particles, they lose energy, allowing the cloud to cool and contract. Over time, gravity takes over, pulling the gas and dust together into denser clumps. These clumps eventually become so dense and hot that nuclear fusion ignites, giving birth to a new star. But cosmic dust doesn't just cool gas clouds. it also acts as a catalyst for the formation of molecules. On the surface of these grains, atoms can come together to form complex molecules like water, carbon monoxide, and even organic compounds. In the cold, dark depths of these clouds, these molecules accumulate, creating the building blocks for future stars and planets. It's a delicate dance of chemistry and physics, one that transforms simple atoms into the raw materials of life. Studying these dusty regions, however, presents a challenge. The same dust that helps form stars also obscures our view, blocking visible light and hiding these processes from traditional telescopes. This is where infrared astronomy comes in. Infrared light, with its longer wavelengths, can penetrate these dusty veils, allowing us to peer into the heart of star-forming regions. Telescopes like the James Webb Space Telescope and the Spitzer Space Telescope have revolutionized our understanding of these cosmic nurseries, capturing stunning images of swirling dust clouds and the infant stars forming within them. These observations have revealed the intricate interplay between dust, gas, and gravity, painting a vivid picture of how stars are born. As we delve deeper into these dusty realms, we begin to see the larger picture. Cosmic dust isn't just a passive participant in the universe's story, it's an active force, shaping the evolution of galaxies and the birth of new worlds. And while these tiny particles may seem insignificant, they remind us that even the smallest elements can have a profound impact on the cosmos. From the formation of stars to the creation of planets, cosmic dust is a testament to the intricate and interconnected nature of the universe. These dusty clouds, however, are just the beginning. Hidden within them are even denser regions known as molecular clouds, where the conditions are perfect for the birth of stars. These clouds, rich in hydrogen molecules and other compounds, are the true cradles of the cosmos, setting the stage for the next chapter in the story of star formation. As we'll explore next, it's within these molecular clouds that the universe's most dazzling phenomena take shape, from the birth of stars to the formation of planetary systems. The journey through these cosmic nurseries is just beginning, and the discoveries waiting to be made are as vast as the universe itself. Nestled within the vast, swirling clouds of cosmic dust are regions so dense and rich with potential that they've earned the name molecular clouds. These colossal structures, spanning hundreds of light years, are the true cradles of star formation. Picture them as cosmic nurseries, where the raw ingredients of the universe, hydrogen, helium, and dust, come together under the influence of gravity to ignite the birth of new stars. It's here, in these cold, dark pockets of space, that the magic of stellar creation begins. The process starts with the tiniest of triggers, an uneven distribution of matter, a shockwave from a nearby supernova, or even the gentle tug of a passing star. These subtle disturbances cause pockets of gas within the molecular cloud to begin collapsing under their own gravity. As the gas condenses, it heats up, forming what's known as a protostar. This embryonic star is still shrouded in a cocoon of gas and dust, but deep within its core, the pressure and temperature are steadily rising. Over hundreds of thousands of years, the protostar grows denser and hotter until finally, nuclear fusion ignites and a new star is born. But the story doesn't end there. As young stars emerge from their dusty cocoons, they begin to shape their surroundings in dramatic ways. Stellar winds, powerful streams of charged particles, blow outward from the star, carving out cavities in the surrounding gas and dust. In some cases, these winds are so intense that they trigger the collapse of nearby gas clouds, sparking the birth of even more stars. It's a cosmic domino effect, where the creation of one star can lead to the birth of many others. Supernova, the explosive deaths of massive stars, also play a crucial role in this process. When a star reaches the end of its life and explodes, it sends shockwaves rippling through the molecular cloud, compressing gas and triggering new rounds of star formation. These explosions also enrich the surrounding space with heavy elements carbon, oxygen, iron, and more, sowing the seeds for future generations of stars and planets. It's a cycle of creation and destruction, where the death of one star gives rise to the birth of many others. Yet, even as young stars shape their environments, they are themselves shaped by the forces around them. The interplay between gravity, radiation, and magnetic fields creates a delicate balance, determining whether a star will grow to be a brilliant giant or a modest dwarf. Over time, these forces guide the star through its life cycle, from its fiery birth to its eventual demise. This journey, known as stellar evolution, is as intricate as it is awe-inspiring, and it's here that we'll find our next chapter in the story of the cosmos. The life of a star is a cosmic journey, one that begins in the cold, dense embrace of a molecular cloud and ends in a blaze of glory, or sometimes in the quiet fade of a stellar ember. But what determines whether a star will burn brightly for billions of years or explode in a spectacular supernova? The answer lies in its mass. From the moment a star ignites, its fate is sealed by the amount of matter it contains. Stars like our Sun, with relatively modest masses, follow a gentle path, while their more massive siblings blaze through life with intensity, leaving behind remnants that defy imagination. For stars like the Sun, the journey begins with nuclear fusion igniting in their cores, where hydrogen atoms fuse into helium, releasing energy that powers the star for billions of years. This stable phase, known as the main sequence, is the longest chapter in a star's life, but eventually the hydrogen in the core runs out and the star begins to change. As helium builds up, the core contracts and heats up while the outer layers expand and cool, transforming the star into a red giant. For our Sun, this phase will mark the end of its life as we know it, as it swells to engulf the inner planets, including Earth. But even in its final act, the Sun will contribute to the cosmos, shedding its outer layers to form a glowing planetary nebula, while its core collapses into a dense white dwarf, a hot, Earth-sized ember that will slowly fade over trillions of years. For more massive stars, the story is far more dramatic. These giants burn through their fuel at an astonishing rate, living fast and dying young. As they exhaust their hydrogen, they begin fusing heavier elements helium into carbon, carbon into oxygen, and so on, each layer of fusion creating a new shell within the star. This process continues until iron forms in the core, a point of no return. Unlike lighter elements, iron cannot release energy through fusion. Instead, it saps energy from the star, causing the core to collapse under its own gravity. In a fraction of a second, the star implodes, then rebounds in a cataclysmic explosion, a supernova. The energy released outshines an entire galaxy, scattering heavy elements forged in the star's core across the universe. These elements, gold, silver, uranium, and more, will one day become part of new stars, planets, and even life itself. But the remnants of these massive stars are just as extraordinary as their deaths. If the core left behind is between 1.5 to 3 times the mass of the Sun, it collapses into a neutron star, a city-sized object so dense that a single teaspoon of its material would weigh billions of tons. Neutron stars spin rapidly, some emitting beams of radiation that sweep across the sky like cosmic lighthouses, earning them the name pulsars. For even more massive stars, the core collapses into a black hole, a region of space where gravity is so strong that not even light can escape. These enigmatic objects warp space-time, creating gravitational waves when they collide and offering us a glimpse into the most extreme environments in the universe. Throughout their lives, stars are more than just celestial objects, they are cosmic forges, creating the elements that make up everything around us. This process, known as nucleosynthesis, begins in the cores of stars and continues through their explosive deaths. From the carbon in our bodies to the iron in our blood, the atoms we're made of were once part of stars that lived and died billions of years ago. In this way, stars are not just distant lights in the sky, they are the ancestors of everything we know. Yet stars rarely live in isolation. Many exist in binary systems, where two stars orbit each other in a delicate dance. These systems can lead to some of the most fascinating phenomena in the cosmos, from the transfer of material between stars to the explosive collisions that create new types of stellar objects. As we'll explore next, binary stars and stellar collisions add another layer of complexity to the story of stellar evolution, revealing a universe that is as interconnected as it is dynamic. Binary star systems are far more common than you might think. In fact, more than half of all stars in the universe are part of a pair, locked in a gravitational dance as they orbit a shared center of mass. These stellar duos range from tightly bound pairs, where stars whirl around each other in just hours, to wide binaries, where the stars are separated by vast distances, taking centuries to complete a single orbit. This intricate interplay of gravity and motion creates a dynamic environment, one that can lead to some of the most spectacular and unusual phenomena in the cosmos. One of the most fascinating aspects of binary star systems is mass transfer. In close binaries, where stars orbit very near to each other, the gravitational pull of one star can strip material away from its companion. This process often forms an accretion disk, a swirling ring of gas and dust around the more massive star. As material spirals inward, it heats up, releasing tremendous amounts of energy. In some cases, this energy is emitted as X-rays, creating what's known as an X-ray binary. These systems are among the brightest X-ray sources in the sky, offering astronomers a window into the extreme physics at play. But mass transfer isn't the only dramatic outcome of binary star systems. When stars in a binary pair are particularly close, their gravitational interactions can lead to collisions. Imagine two stars, each with their own immense gravitational pull, spiraling closer and closer until they merge in a fiery explosion. These stellar collisions are rare, but when they occur, they release an astonishing amount of energy, briefly outshining entire galaxies. The aftermath of such events can produce exotic objects, like blue straggler stars that appear younger and more massive than their surroundings, rejuvenated by the collision. Binary stars also play a crucial role in one of the most important events in astronomy, Type Ia supernova. These explosions occur when a white dwarf, the dense remnant of a star like our Sun, orbits a companion star. If the white dwarf pulls enough material from its partner, it can reach a critical mass, triggering a runaway thermonuclear explosion. Type Ia supernova are so bright and consistent that they are used as standard candles to measure distances across the universe. Without binary stars, these cosmic mileposts wouldn't exist, and our understanding of the universe's scale would be far less precise. The study of binary stars doesn't just reveal the lives and deaths of stars, it also connects to the search for planets beyond our solar system. Many exoplanets, or planets orbiting other stars, have been discovered in binary systems. In some cases, these planets orbit one of the stars, while in others, they orbit both stars in what's known as a circumbinary orbit. Picture a planet with two suns, like Tatooine from Star Wars. These exotic worlds challenge our understanding of planet formation and stability, offering a glimpse into the incredible diversity of planetary systems. As we continue to explore the cosmos, binary stars remind us that the universe is a place of endless complexity and wonder. From the gentle dance of wide binaries to the explosive collisions of close pairs, these systems shape the evolution of galaxies and the lives of countless stars and planets. And as we turn our attention to exoplanets, we'll see how these distant worlds, born in the crucible of stellar systems, hold the key to understanding not just the universe, but our place within it. The discovery of exoplanets' worlds orbiting stars beyond our solar system has revolutionized our understanding of the cosmos. Before the 1990s, the only planets we knew of were the ones circling our own sun. But today, thanks to advances in technology and ingenuity, thousands of exoplanets have been confirmed, with countless more waiting to be discovered. These distant worlds come in all shapes and sizes, from scorching gas giants to rocky super-Earths, each one offering a glimpse into the incredible diversity of planetary systems across the galaxy. So, how do we find these distant worlds? One of the most effective methods is the transit technique. Imagine a planet passing in front of its star, like a tiny shadow crossing a bright light. As the planet transits, it blocks a small fraction of the star's light, causing a subtle dip in brightness that astronomers can detect. This method not only reveals the presence of a planet, but also provides clues about its size, orbit, and even its atmosphere. The Kepler Space Telescope, a pioneer in this field, used the transit method to discover thousands of exoplanets, transforming our understanding of how common planets are in the universe. Another key technique is radial velocity, which measures the wobble of a star caused by the gravitational pull of an orbiting planet. As a planet tugs on its star, the star moves slightly toward and away from us, causing its light to shift in wavelength, a phenomenon known as the Doppler effect. By studying these shifts, astronomers can determine a planet's mass and orbital period. Together, the transit and radial velocity methods have opened a new frontier in astronomy, allowing us to detect and characterize planets that were once beyond our reach. The diversity of exoplanets is staggering. Some are gas giants, many times larger than Jupiter, orbiting so close to their stars that their atmospheres are scorched and stripped away. Others are rocky super-Earths, larger than our planet but potentially similar in composition. Then there are the intriguing mini-Neptunes, shrouded in thick atmospheres of hydrogen and helium, and the enigmatic hot Jupiters, gas giants that defy expectations by hugging their stars in tight, fiery orbits. Each discovery challenges our assumptions and expands our understanding of what planets can be. But among these countless worlds, one question looms large: could any of them support life? The search for potentially habitable exoplanets, those with conditions that might allow liquid water to exist, is one of the most exciting areas of research. Planets like Proxima Centauri b, orbiting within the habitable zone of its star, offer tantalizing possibilities. Others, like the TRAPPIST-1 system, host multiple Earth-sized planets, some of which may have the right conditions for life. While we haven't yet found definitive proof of habitability, each discovery brings us closer to answering one of humanity's oldest questions: are we alone? As we uncover more about these distant worlds, we're also learning how they fit into the broader story of galaxy formation. Planetary systems aren't isolated phenomena. They are part of the intricate web of cosmic evolution, shaped by the same forces that create stars and galaxies. From the swirling disks of gas and dust around young stars to the gravitational dances of binary systems, the formation of planets is deeply intertwined with the life cycle of their host stars and the galaxies they inhabit. And as we'll explore next, this connection between planets, stars, and galaxies reveals a universe that is not just vast and diverse, but profoundly interconnected. As we explore the vast array of exoplanets scattered across the cosmos, it's impossible to ignore the broader stage on which these planetary systems are formed, the galaxy itself. Planetary systems don't exist in isolation. They're deeply connected to the life cycle of their host stars and the intricate dynamics of the galaxy they call home. From the swirling disks of gas and dust, where planets are born to the gravitational forces that shape their orbits, the story of planetary systems is woven into the fabric of galactic evolution. But how exactly does the galactic environment influence these systems? And what role does the galaxy play in their creation and survival? Let's start with the birth of planetary systems. Most stars, and by extension the planets that orbit them, form in the dense, turbulent regions of molecular clouds. These clouds, rich in gas and dust, are scattered throughout galaxies, often concentrated in the spiral arms of disk galaxies like our Milky Way. As gravity pulls these clouds together, they fragment into smaller clumps, each one collapsing to form a star surrounded by a swirling disk of material. It's within these disks that planets begin to take shape, coalescing from the dust and gas that remain after the star's formation. But the story doesn't end there. The galactic environment plays a crucial role in shaping these disks and ultimately the planets that form within them. One key factor is the galaxy's chemical composition, often referred to as its metallicity. This term, in astronomy, refers to the abundance of elements heavier than hydrogen and helium, elements like carbon, oxygen, and iron that are essential for planet formation. Galaxies with higher metallicity tend to produce more planets, as these elements are the building blocks of rocky worlds and the cores of gas giants. In regions of the galaxy where metallicity is lower, planet formation is less common, and the planets that do form may be smaller or less diverse. This connection between galactic chemistry and planetary systems highlights how deeply intertwined they are, with the galaxy's history leaving a lasting imprint on its planets. But it's not just chemistry that shapes planetary systems. It's also the galaxy's dynamic environment. Stars and their planets don't stay in one place. They move through the galaxy, influenced by its gravitational field and the interactions of neighboring stars. In crowded regions, such as the galactic center, close encounters between stars can disrupt planetary systems, flinging planets out of their orbits or even ejecting them into the void of interstellar space. In quieter regions, like the outskirts of the galaxy, planetary systems may evolve more peacefully, giving planets the stability they need to develop and potentially support life. Galactic collisions and interactions add another layer of complexity to this story. When galaxies collide, a process that can take hundreds of millions of years, the gravitational forces at play can trigger bursts of star formation, creating new planetary systems in the process. These collisions also redistribute gas and dust, enriching the galactic environment with the raw materials needed for planet formation. The resulting chaos can reshape entire regions of the galaxy, creating new opportunities for planets to form while disrupting others. It's a cosmic dance of creation and destruction, where the fate of planetary systems is shaped by the movements of the galaxies themselves. This brings us to a fascinating concept: galactic cannibalism. Just as planets can be influenced by their galactic environment, galaxies themselves can grow and evolve by consuming smaller neighbors. When a large galaxy interacts with a smaller one, its immense gravitational pull can strip away stars, gas, and even entire planetary systems from the smaller galaxy, incorporating them into its own structure. This process, known as galactic cannibalism, is one of the ways galaxies grow over time, building their mass and diversity by absorbing others. The Milky Way, for example, has a history of such interactions, with evidence of past mergers visible in the distribution of stars and the remnants of smaller galaxies orbiting its outskirts. The impact of galactic cannibalism goes beyond just the growth of galaxies. It also influences the distribution and evolution of planetary systems. As stars and their planets are pulled into a larger galaxy, they become part of its dynamic environment, subject to its gravitational tides and the interactions of its many stars. This can lead to the reshuffling of planetary orbits, the creation of new stars and planets, and the disruption of existing systems. It's a reminder that the universe is a place of constant change, where even the largest structures are shaped by the forces of gravity and time. As we continue to explore the connections between planetary systems and their galactic context, one thing becomes clear: the universe is a deeply interconnected web, where the smallest planets and the largest galaxies are bound together by the same fundamental forces. From the chemistry of star-forming clouds to the gravitational ballet of galactic collisions, every piece of the puzzle plays a role in shaping the cosmos we see today. And as we'll see next, this interconnectedness extends even further, revealing a universe where the past, present, and future are woven together in a single, grand tapestry. Galaxies, like living organisms, are shaped by their interactions, sometimes gentle, often violent. Among the most dramatic of these interactions is a process known as galactic cannibalism, where larger galaxies devour smaller ones through the relentless pull of gravity. Picture a cosmic predator, its immense gravitational field tearing apart a smaller galaxy, absorbing its stars, gas, and even its planetary systems. This isn't a rare event. It's a fundamental part of how galaxies grow and evolve over billions of years. In fact, our own Milky Way has a history of such encounters, with remnants of smaller galaxies still visible in its outer reaches. These interactions, while destructive, are also creative, reshaping galaxies in ways that leave lasting imprints on their structure and composition. When galaxies collide, the results can be both chaotic and beautiful. As the smaller galaxy is pulled apart, its stars are scattered, forming streams and arcs that stretch across the sky. These structures, known as tidal tails, are like cosmic brushstrokes, painting the aftermath of a galactic feast, but the effects go far beyond just visual spectacle. The gas and dust stripped from the smaller galaxy can trigger bursts of star formation, lighting up the larger galaxy with newborn stars. These starbursts are some of the most intense and luminous events in the universe, transforming the galactic landscape in a blaze of cosmic fireworks. Yet, even as new stars are born, the collision can also disrupt existing planetary systems, flinging planets into new orbits or even ejecting them into the void of interstellar space. One of the most intriguing outcomes of galactic mergers is the formation of elliptical galaxies. Unlike the graceful spirals we often picture, elliptical galaxies are smooth, featureless collections of stars, shaped more like footballs than pinwheels. These galaxies are thought to form when two spiral galaxies collide and merge, their gas and dust compressed and heated until star formation slows to a crawl. What's left is a dense, aging population of stars, orbiting in random directions. Elliptical galaxies are often found at the centers of galaxy clusters, where mergers are more frequent, serving as a testament to the transformative power of galactic collisions. At the heart of these merging galaxies lies another dramatic player, supermassive black holes. As galaxies collide, their central black holes are drawn together, eventually merging into an even more massive object. This process releases staggering amounts of energy, often in the form of gravitational waves, ripples in space-time that can be detected by observatories like LIGO. These mergers also trigger intense bursts of radiation, as gas and dust swirl around the black holes, heating up and glowing brightly. In some cases, the merged black hole becomes the engine of an active galactic nucleus, a powerhouse of energy that can outshine an entire galaxy. These active nuclei play a crucial role in shaping their host galaxies, influencing star formation and the distribution of gas on galactic scales. Yet, the story of galactic mergers doesn't end with the black holes. The energy released during these collisions can heat up the surrounding gas, preventing it from collapsing to form new stars. This process, known as feedback, helps regulate the growth of galaxies, ensuring they don't grow too large too quickly. It's a delicate balance, one that underscores the interconnected nature of the cosmos, where even the most violent events can have a stabilizing effect. As we shift our focus from the chaos of galactic cannibalism to the role of active galactic nuclei, we'll see how these energetic powerhouses continue to shape the evolution of galaxies, driving their growth and influencing their ultimate fate. The universe, it seems, is a place of both creation and destruction, where every collision and merger leaves a lasting mark on the cosmic tapestry. And as we delve deeper into these mysteries, we're reminded that the story of the cosmos is far from over. It's a dynamic, ever-changing narrative, waiting for us to uncover its next chapter. At the heart of some of the most energetic and luminous galaxies lies a phenomenon so powerful it can outshine billions of stars combined. These are active galactic nuclei, or AN, the brilliant cores of galaxies fueled by supermassive black holes. Imagine a cosmic engine voraciously consuming gas, dust, and even stars, while releasing torrents of energy that can shape the destiny of an entire galaxy. This isn't just a fleeting burst of light, it's a sustained outpouring of energy driven by the immense gravitational forces at play within the black hole's grasp. But not all AGN are the same. Their diversity is as fascinating as their power, with each type offering a unique window into the extreme physics of the universe. One of the most spectacular forms of AGN is the quasar. These are the brightest objects in the cosmos, capable of shining with the light of 1 trillion stars. Quasars are so luminous that they can be seen from billions of light years away, their light traveling across the universe to reach us. But what makes them so bright? The answer lies in the supermassive black hole at their core. As matter spirals into the black hole, it forms a swirling disk of superheated gas, glowing intensely before vanishing into the event horizon. This process, known as accretion, releases staggering amounts of energy, lighting up the quasar like a cosmic beacon. Yet, despite their brilliance, quasars are relatively short-lived, burning brightly for just a few million years before their fuel runs out. Seyfert galaxies, on the other hand, are a quieter but no less intriguing class of AGN. These galaxies, first identified by astronomer Carl Seyfert in the 1940s, have bright, compact cores that shine with the light of ionized gas. Unlike quasars, Seyfert galaxies are visible across a range of wavelengths, from radio waves to X-rays, revealing the complex processes at work around their central black holes. Some Seyfert galaxies are surrounded by rings of glowing gas, while others show jets of material spewing outward at incredible speeds. These jets, powered by the black hole's magnetic fields, can extend far beyond the galaxy itself, carving out vast bubbles in the surrounding gas. Then there are blazars, the most extreme members of the AGN family. These objects are essentially quasars with their jets pointed directly at Earth, making them some of the most energetic phenomena in the universe. Blazars emit intense bursts of gamma rays and other high-energy radiation, creating a dazzling display that can outshine entire galaxies. Their jets, traveling at nearly the speed of light, are thought to be powered by the black hole's spin and magnetic fields, offering a glimpse into the extreme conditions near the event horizon. But AGN aren't just cosmic light shows, they play a crucial role in shaping their host galaxies. Through a process known as feedback, the energy released by AGN can heat up and expel gas from the galaxy, regulating star formation and influencing the galaxy's evolution. In some cases, this feedback can completely shut down star formation, leaving the galaxy to age in relative quiet. In others, it can trigger bursts of new star birth, reigniting the galaxy with fresh activity. Outflows of gas, driven by the AGN's powerful jets and winds, can also redistribute material across the galaxy, seeding the formation of new stars and planets. The influence of AGN extends even further, shaping the large-scale structure of the universe itself. By heating and redistributing gas within galaxy clusters, AGN help regulate the growth of these colossal structures, ensuring they don't become too massive too quickly. This delicate balance between creation and destruction, driven by the interplay of gravity and energy, is one of the key forces shaping the cosmos. As we turn our attention to galaxy clusters, we'll see how these vast assemblies of galaxies, gas, and dark matter are woven together into the intricate web that defines the universe on the largest scales. From the brilliance of AGN to the cosmic tapestry of galaxy clusters, the story of the universe is one of connection, balance, and endless wonder. Galaxy clusters are the titans of the cosmos' vast metropolises, where thousands of galaxies gather, bound together by the unyielding grip of gravity. These colossal structures are more than just collections of stars and gas. They are the largest gravitationally bound systems in the universe, serving as both anchors and crossroads in the cosmic web. Imagine a bustling city, but instead of skyscrapers, you see galaxies of all shapes and sizes, swirling in a cosmic dance that has lasted billions of years. These clusters are the beating hearts of the universe's large-scale structure, guiding the flow of matter and energy on the grandest scales. At the heart of every galaxy cluster lies a hidden force, dark matter. This mysterious substance, invisible yet omnipresent, makes up the majority of a cluster's mass. Its gravitational pull holds the cluster together, acting as the cosmic glue that keeps galaxies from drifting apart. Without dark matter, these colossal structures would simply fly apart, their galaxies scattering into the void. The presence of dark matter isn't just inferred, it's revealed by the way galaxies move within the cluster, their motions betraying the unseen hand that shapes their paths. Mapping this invisible web is one of the great challenges of modern cosmology, offering clues about the nature of dark matter and its role in the universe's evolution. But dark matter isn't the only player in galaxy clusters. Filling the spaces between galaxies is hot gas, heated to millions of degrees and glowing faintly in X-ray light. This intracluster medium, as it's called, is a diffuse atmosphere that permeates the entire cluster. How does it get so hot? The answer lies in the immense gravitational pull of the cluster itself. As galaxies move through this environment, their motion stirs the gas, generating shockwaves that heat it to incredible temperatures. This hot gas isn't just a byproduct. It plays a crucial role in the cluster's evolution, influencing star formation and the growth of galaxies within it. It's a dynamic, ever-changing environment, shaped by the interplay of gravity, gas, and dark matter. One of the most dramatic events in the life of a galaxy cluster is a collision with another cluster. When two clusters meet, the result is one of the most energetic events in the universe. The collision releases staggering amounts of energy, heating the gas to even higher temperatures and creating shock waves that ripple through the cluster. These collisions can also strip gas from galaxies, altering their evolution and leaving behind ghostly trails of material. It's a cosmic spectacle, a reminder that even the largest structures in the universe are shaped by forces beyond our everyday experience. The Bullet Cluster, for example, provides a stunning example of such a collision, with its dark matter and gas separated by the immense forces at play. Yet, galaxy clusters are more than just cosmic laboratories for studying dark matter and gas. They're also key to understanding the universe's expansion. By measuring the distribution and motion of clusters, astronomers can probe the properties of dark energy, the mysterious force driving the universe's accelerated expansion. Clusters act as cosmic mileposts, their growth and distribution offering clues about how dark energy has shaped the universe over billions of years. It's a complex puzzle, one that requires piecing together observations from across the electromagnetic spectrum, from X-rays to radio waves, to build a complete picture of the cosmos. But the story of the large-scale universe doesn't end with galaxy clusters. Between these titanic structures lie vast, nearly empty regions known as cosmic voids. These voids, spanning hundreds of millions of light years, are the flip side of the cosmic web regions where matter is sparse and galaxies are few and far between. Yet, despite their emptiness, voids play a crucial role in the universe's structure. They act as cosmic pressure chambers, their low density allowing galaxies and clusters to flow toward denser regions, shaping the web of filaments and nodes that define the large-scale universe. Voids are also key to understanding the distribution of dark energy, as their growth and evolution are influenced by the same forces that drive the universe's expansion. As we explore these vast, empty regions, we're reminded that the universe is a place of both structure and emptiness, of light and shadow. From the bustling cities of galaxy clusters to the quiet expanses of cosmic voids, every part of the cosmos plays a role in the grand story of the universe. And as we delve deeper into these mysteries, we're left with a profound sense of connection to the forces that shape the cosmos, to the galaxies that fill the night sky, and to the questions that drive us to explore further. The universe, it seems, is far more than the sum of its parts. It's a dynamic, ever-changing tapestry, waiting for us to uncover its next chapter. Between the bustling galaxy clusters and the intricate filaments of the cosmic web lies a realm of profound emptiness, cosmic voids. These vast regions, stretching hundreds of millions of light years across, are the universe's quietest corners, where galaxies are sparse and the density of matter is strikingly low. Yet, despite their apparent emptiness, cosmic voids are far from insignificant. They are an essential part of the cosmic web, shaping the universe on the largest scales and offering unique insights into the forces that govern its evolution. Understanding these voids is like exploring the silent spaces between the notes in a symphony. They may seem empty, but they hold the key to the music's structure and rhythm. The formation of cosmic voids begins with the same tiny fluctuations in density that gave rise to galaxies and clusters. In the early universe, regions with slightly less matter expanded faster than their denser counterparts, creating vast, underdense areas. Over billions of years, gravity pulled matter away from these regions and into the surrounding filaments, leaving behind the voids we see today. These voids aren't completely empty. They still contain a scattering of galaxies, gas, and dark matter. But their density is so low that they appear as dark, empty expanses against the backdrop of the cosmic web. It's a cosmic balancing act, where the emptiness of voids is just as important as the density of galaxies and clusters. Studying these seemingly barren regions, however, presents unique challenges. With so few galaxies to observe, astronomers must rely on indirect methods to probe the properties of voids. One such method is gravitational lensing, where the light from distant objects is bent by the gravitational influence of matter within the void. By measuring these subtle distortions, scientists can map the distribution of dark matter in voids, shedding light on their structure and evolution. Another approach is to study the faint glow of the cosmic microwave background, the afterglow of the Big Bang, which carries imprints of the void's effects on the universe's early expansion. These techniques reveal that voids are not just passive gaps. They are dynamic regions, expanding faster than the rest of the universe and influencing the growth of the cosmic web. Cosmic voids also play a crucial role in our understanding of dark energy, the mysterious force driving the universe's accelerated expansion. Because voids are less dense, they are more sensitive to the effects of dark energy, acting as cosmic laboratories where its influence can be measured. By studying how voids grow and evolve, astronomers can test theories about the nature of dark energy and its impact on the universe's fate. These seemingly empty regions, then, are far from irrelevant. They are windows into the fundamental forces that shape the cosmos. Yet, the significance of cosmic voids extends beyond cosmology. They challenge our perception of the universe, reminding us that emptiness is not the absence of meaning, but a vital part of the cosmic tapestry. Just as the spaces between words give language its structure, the voids between galaxies define the architecture of the universe. They are a testament to the delicate balance of creation and emptiness, of structure and space, that underlies everything we see. As we turn our gaze from the emptiness of cosmic voids to the future of space exploration, we're reminded that the universe is full of mysteries waiting to be uncovered. The tools and technologies we've developed, from gravitational lensing to space-based telescopes, are opening new doors to discovery, allowing us to probe the farthest reaches of the cosmos and the deepest questions about its origins. What lies ahead is not just a continuation of our journey, but a new chapter in our quest to understand the universe and our place within it. The story of the cosmos is far from over, and the next discoveries may be closer than we think. The future of space exploration is not just a continuation of our journey, it's a leap into the unknown, a bold step toward unraveling the universe's deepest mysteries. Imagine a world where missions to distant exoplanets are no longer the stuff of science fiction, but a regular part of our scientific endeavors. Picture telescopes so advanced they can peer into the atmospheres of worlds light years away, searching for signs of life or clues about the origins of the cosmos. This isn't just a dream, it's the direction we're heading, driven by cutting-edge technology, international collaboration, and an insatiable curiosity about the universe. One of the most exciting frontiers lies in the search for habitable exoplanets. Missions like the James Webb Space Telescope are already transforming our ability to study distant worlds, analyzing their atmospheres for biosignatures, chemical traces that could indicate the presence of life. But the next generation of telescopes, like the Extremely Large Telescope and the Nancy Grace Roman Space Telescope, will take this even further. With unprecedented resolution and sensitivity, these instruments could detect not just the presence of water or oxygen, but also more complex molecules that might hint at biological activity. The discovery of extraterrestrial life, even in microbial form, would be one of the most profound moments in human history, reshaping our understanding of biology, evolution, and our place in the cosmos. But the search for life isn't the only goal. Future missions aim to explore the outer reaches of our solar system and beyond. Projects like NASA's Dragonfly mission will send a robotic rotorcraft to explore the surface of Titan, Saturn's moon, with its thick atmosphere and methane lakes. Meanwhile, missions to Europa and Enceladus, moons with subsurface oceans, could reveal whether these icy worlds harbor life beneath their frozen crusts. These missions aren't just about answering scientific questions, they're about pushing the boundaries of what's possible, demonstrating humanity's ability to explore even the most hostile environments. At the same time, the next generation of space-based observatories will revolutionize our understanding of the universe's most enigmatic components, dark matter and dark energy. The Vera C. Rubin Observatory, set to begin operations in the coming years, will map the cosmos in unprecedented detail, shedding light on the distribution of dark matter and the effects of dark energy on the universe's expansion. Meanwhile, missions like ESA's Euclid and NASA's Nancy Grace Roman Space Telescope will probe the nature of these mysterious forces, offering clues about their origins and their impact on the universe's fate. These discoveries could fundamentally alter our understanding of physics, revealing new laws of nature and perhaps even new dimensions of reality. Yet, these ambitious goals require more than just technological innovation. They demand a collective commitment to science and exploration. Continued investment in research, education, and international collaboration is essential to unlocking the universe's secrets. Space exploration isn't just about answering scientific questions. It's about inspiring future generations, fostering global cooperation, and reminding us of our shared humanity. Every mission, every discovery, is a testament to what we can achieve when we work together toward a common goal. As we look to the future, it's impossible not to reflect on our place in the universe. The cosmos is vast, filled with wonders and mysteries that challenge our understanding and ignite our imagination. Yet, in the face of this immensity, we are not insignificant. Our curiosity, our ingenuity, and our determination to explore the unknown are what make us unique. Every telescope we build, every mission we launch, is a declaration that we are part of something greater, a universe that invites us to explore, to question, and to dream. And as we continue this journey, we're reminded that the story of the cosmos is not just about stars and galaxies. It's about us and our endless quest to understand the universe and our place within it. As we stand on the brink of a new era of cosmic discovery, it's worth pausing to reflect on what all of this means for us, not just as scientists or explorers, but as human beings. The universe, with its billions of galaxies, trillions of stars, and countless worlds, is a stage so vast it defies comprehension. Yet here we are, a tiny species on a pale blue dot, daring to ask questions, to seek answers, and to reach out into the unknown. What does this say about our place in the cosmos? Are we insignificant, or does our capacity to understand the universe give us a unique role in its unfolding story? The sheer scale of the universe can be overwhelming. When we look at the night sky, we're seeing light that has traveled for millions, or even billions, of years to reach us. Every star, every galaxy, tells a story of time and distance that stretches the limits of our imagination. In the face of such vastness, it's easy to feel small, even inconsequential. But there's another way to look at it. The fact that we can observe, measure, and even begin to understand the cosmos is nothing short of extraordinary. Our ability to unravel the mysteries of the universe, to peer into the hearts of stars, to map the invisible threads of dark matter, to dream of life beyond Earth sets us apart. It's a testament to the power of curiosity, creativity, and collaboration. This journey of discovery isn't just about satisfying our curiosity, it's also about understanding our origins and our future. The atoms that make up our bodies were forged in the cores of ancient stars, scattered across the cosmos by supernovae, and gathered together on a planet orbiting an unremarkable star in a quiet corner of the Milky Way. In that sense, we are deeply connected to the universe, not just as observers, but as participants in its grand narrative. The same forces that shaped galaxies and stars have also shaped us, and the story of the cosmos is, in many ways, our story too. Yet, with this understanding comes a profound responsibility. As we uncover the secrets of the universe, we're also confronted with the fragility of our own planet. Earth, with its delicate balance of ecosystems, is the only home we have. The same ingenuity that allows us to explore the cosmos must also be directed toward preserving and protecting our world. Climate change, pollution, and habitat destruction are challenges that demand our attention, reminding us that our quest for knowledge must be paired with a commitment to stewardship. The universe may be infinite, but our time here is finite, and the choices we make today will shape the future of our species and our planet. These discoveries also raise existential questions that have puzzled philosophers and scientists for centuries. Are we alone in the universe? What is the purpose of life in a cosmos that seems indifferent to our existence? While we may not have definitive answers, the search itself is meaningful. It pushes us to think deeply about who we are, where we come from, and where we're headed. The universe doesn't provide easy answers, but it invites us to ask better questions, to challenge our assumptions, and to embrace the unknown. As we reach the end of this journey through the cosmic realms, it's clear that the story of the universe is still being written. From the first stars to the galaxies that light up the night sky, from the invisible threads of dark matter to the explosive energy of supernova, every discovery adds a new chapter to this epic tale. And while the universe may seem vast and impersonal, it's also a source of endless wonder and inspiration. It reminds us that we are part of something greater, connected to the cosmos in ways we're only beginning to understand. So, what's next? The answer lies not just in the stars, but within us. The tools we've built, the knowledge we've gained, and the questions we've asked are all steps on a journey that has no end. The universe is vast, but so is our potential. As we continue to explore, to learn, and to dream, we're not just uncovering the secrets of the cosmos, we're also discovering what it means to be human. And in that discovery, perhaps, lies the greatest mystery of all. As we reach the end of our voyage through the celestial realms, it's worth taking a moment to reflect on the incredible journey we've shared. From the fiery birth of the first stars in the cosmic dark ages to the sprawling galaxies that light up our modern skies, we've traced the evolution of the universe across billions of years. We've explored how ancient supernovae seeded the cosmos with the elements that make up our world, how galaxies collide and merge in a cosmic dance of creation and destruction, and how mysterious forces like dark matter and dark energy shape the very fabric of reality. Each discovery has revealed a universe that is not just vast and beautiful, but deeply interconnected, a tapestry where every thread, from the smallest particle to the largest galaxy, plays a vital role. The scale of the universe is almost beyond comprehension. When we look at the night sky, we're not just seeing distant stars, we're peering into the past, witnessing light that has traveled across unfathomable distances to reach us. It's a humbling reminder of how small we are in the grand scheme of things, yet it's also a testament to the extraordinary progress humanity has made in understanding the cosmos. From the first telescopes that revealed the moons of Jupiter to the cutting-edge observatories that map the cosmic web, our tools and curiosity have brought us closer to answering some of the universe's most profound questions. And while there's still so much we don't know, every discovery brings us one step closer to unraveling the mysteries that have captivated us for centuries. But this journey isn't just about the universe, it's about us. The atoms in our bodies, the air we breathe, and the ground we walk on were all forged in the hearts of stars, scattered across the cosmos, and gathered together on this pale blue dot we call home. In that sense, we are as much a part of the universe as the stars themselves. This connection, this shared cosmic heritage, is what makes the study of the cosmos so deeply personal. It's not just about understanding the universe, it's about understanding ourselves and our place within it. As we close this chapter, let's carry forward the sense of wonder and curiosity that has guided us. Whether it's through stargazing on a clear night, diving into the latest discoveries in astronomy, or supporting the scientific endeavors that push the boundaries of our knowledge, there are countless ways to keep exploring the cosmos. The universe is a story that's still being written, and each of us has a role to play in uncovering its secrets. To leave you with a thought, consider the words of Carl Sagan: "Somewhere, something incredible is waiting to be known." The universe is full of wonders, from the smallest particles to the largest galaxies, and the journey to discover them is one of the greatest adventures humanity has ever undertaken. So, let's keep looking up, keep asking questions, and keep marveling at the beauty and complexity of the cosmos. If you've enjoyed this journey through the celestial realms, don't forget to subscribe to the channel for more explorations into the mysteries of the universe. Share your thoughts in the comments. What part of this cosmic story fascinated you the most? Let's build a community of curious minds, united by our shared love for the stars and the stories they tell. Together, we can keep exploring, learning, and dreaming of what lies beyond the horizon. The universe is waiting. Let's